All right, when we want to look for evidences for macroevolution from the field of paleontology, that's the study of fossils. Looking at the fossil record here, the first thing we want to bring up is the concept of superposition. We could say superposition of sedimentary rock or sediments or whatever, but anyway, basically what it means is that as material goes to the ground or goes to the bottom of a lake or the ocean or whatever, those things that settle into the bottom when they die, they'll be covered up by new sands and silts and other layers of material over time, and additional material will form on top of that. Then new fossil forming organisms will come in and lay on top of that material, and then more sediments will come in on top of that. So we're just layering sediments over time from deeper layers to more recent layers. So you say you start out with a low area, it could be a lake or just could be just a low area that gets filled in with sand and other material. But anyway, you get this layer of material to form down in here from sediments. So your first sedimentary layer forms here, and over time more sediments will be added to that. So you get another layer of sediment. Let's put a cross hatching on this layer here that covers up the first layer of material. Then more material is going to end up coming in, laying on top of that, so you end up with a third layer of sedimentary material, and over time these get compressed and form solid rocks. They may be like shale material or limestone or sandstones or whatever, but anyway, they accumulate on top of one another, so that those things that are found more deeply in the sedimentary bed down here are obviously older than those fossils that would form in layers above that. So this concept of superposition allows us to do some rough estimation of relative age of the different fossil forms you find in these rock formations. So those things that are deepest in the sedimentary layers are considered to be the older fossils, and those things that are up are newer fossils. Now, in agreement with that, we find things that are more unlike the things on Earth today, the more dissimilar kinds of organisms, more of those down deeper in the sedimentary rocks, things like trilobites or ammonites would be way down in this layer. They're no longer on the Earth's surface down here. And then more recent things would be up on top of that. Okay? So our things that are in our most recent fossil beds, the youngest fossil beds, are more similar to life on Earth today than those things that are deeper in the fossil record. So the law of superposition just says that newer things are on top of older things in the arrangement of fossil layers on the Earth's surface. The law of or concept of superposition. Okay? All right, now in this next example, remember we talked last time about, in the last screen we had here, about how we can age things relatively by what layer of sediment they are in. Older things are deeper, younger things are higher in the sedimentary layers, but how do you get an age, an approximation of how old something is in a fossil bed? And this is what we're going to talk about now. Evidences for evolution from the fossil record using radiometric dating techniques. We're going to be looking at the decay of unstable isotopes, chemicals that are atoms that are not stable in their current state and will undergo a change, and it takes a certain amount of time for that particular change in their configuration. What we call a half-life is where half of the material in the sample degrades to another form of the atom over time. So we start here with our first example. We're going to use this carbon-14. Carbon-14 changes to nitrogen-14. Takes approximately 5,730 years for half of that carbon-14 to degrade. Now, carbon-14 is in a fairly constant proportion to all the other carbon in nature, in the atmosphere, and in living things on the Earth's surface. So anyway, we've kind of got this mix of this carbon-14 along with carbon-12 in the environment around us. When an animal dies or when any organic material stops living, that material will begin this degradation, the isotope form of carbon-14. Half of it will change over to nitrogen-14 in 5,730 years. So if you look at the ratios of carbon-14 to carbon-12, to kind of tell you where you are in relation to what living things would have in it. Anyway, the half-life is 5,730 years. This is not very good for dating things that are like millions of years old or even hundreds and hundreds of thousands of years old with its short half-life of 5,730 years. Okay, so it's pretty good for dating, say, the Dead Sea Scrolls or some other artifacts, some bone you dig out of some archaeological pit, old pottery, things related to old pottery and so on. So that kind of dating, more recent material that forms in the sediments that you can find in sedimentary layers can be dated using carbon-14, but when you get very old, and most of the fossils we talk about are much older, you're going to have to use one of these other forms of unstable element, like uranium-235 that degrades to lead-207 in 704 million years. So that will account for just about anything on the planet. So anything you want to estimate a date for, you can, if you can find uranium-235 degrading to 207 in the sample, then you'll be okay. Now, part of the problem with this is that sedimentary layers are made up of individual tiny particles from rocks and materials that are on the Earth's surface that are of all different kinds of ages. So the materials that form these sedimentary layers are hard to date using these types of isotopes, this uranium or the potassium-40 example that I have here. So the molten rock found deep in the Earth has a fairly predictable amount of uranium-235 to lead-207 present in it, and it's kind of mixed up in the molten rock of the Earth. So when that molten rock comes closer to the surface and cools, forms a solid rock that's going to stay there and not be remixed with everything else, we can begin the dating process. And a better way, even a more important way to us, is the existence of lava that extends up to the Earth's surface and forms a lava flow over the surface of sedimentary layers, or intrudes between layers of rock, found in between layers of sedimentary rock, or forms volcanic ash that falls out on the surface of the ground. So any of those kinds of volcanic molten rock events that come through the surface, through those layers of sedimentary rock that have the fossils, those can help us to begin the dating process for those sedimentary layers. So we don't date the sedimentary layer itself, we date that lava intrusion or lava flow or ash deposit in the layered rock. Okay? So if we know that based on our uranium-235 estimation that we have a layer of lava that flowed out onto the surface, say 175 million years ago, according to the decay rate, anything below that lava flow would be older than 175 million years. Those sediments, any sedimentary layers down there, would be older than 175 million years. Anything above that, any sedimentary layers laid down on top of that lava flow would be younger, newer than the 175 million years. So we get these relative ages. A sedimentary bed is between this age and this age, based on what we know from the igneous rocks or lava flows and so on that are adjacent to that material. So that will help us age our sedimentary beds. If we don't have any igneous intrusions, any lava flows or anything in any of the material close to those sedimentary beds, then we have more problems in figuring out exactly what the age or date should be for that particular strata of rock. So anyway, this is a little bit of how we do the estimating of the ages of the sedimentary beds. We can't age them directly using uranium or potassium-40 methods. But we can, if we have the lava flows, ash flows, or intrusions of igneous rock between layers, we can get some estimation on the age of the sedimentary beds. So I thought I'd use this illustration from the web page, our web page, to show a little bit how we use this igneous rock to estimate the age of sedimentary layers. And in black here we have molten rock that has pushed up in between layers here, passed through this layer of sediment, and then formed a layer between these two layers of sedimentary rock. This is what I call an igneous intrusion. It's intruded between layers of rock, kind of separated those layers. Up here we have a lava flow where lava came out on the surface and spread across the ground, and it was covered up with a layer of sediment, and then on top of that sedimentary layer we have a little bit of volcanic ash. So any of these, the volcanic ash, the lava flow, or the intrusion, the igneous intrusion, may have rock that can be more accurately estimated in age using uranium or potassium methods. So that we know that if this rock was intruded through by the magma coming up from below, we know that this rock has to be older than that intrusion there. And this rock that's above it could also be older because this is an intrusion between the two. We know that the rock below this lava flow has to be older than the lava flow, and that's on top of it has to be younger. We know that it's younger than this lava flow, but it's older than the volcanic ash that came in on top of it. So we can kind of bracket the age of that sedimentary layer based on those two examples. Our next topic with regard to fossils is the use of index fossils. Index fossils are fossils that can be used to infer the age of a sedimentary bed in some distant location with same kinds of fossils. So rock beds with similar fossils are assumed to be approximately of the same age, the same geologic time frame anyhow. If they contain the same kinds of fossils from two different locations, they can be assigned the same age. So if you know the age of the sedimentary bed based on isotope dating, possibly, in one location on the Earth's surface, and you go to some other continent, some distant location, and you find other sedimentary layers, those that have the same kinds of fossils, but there's no other way of dating that layer, you can well, what we do is assign that age to the known fossil layers that have the same fossil somewhere else. At least until we find some contradictory evidence. That's the best way to estimate the age of a sedimentary layer based on fossils, using the index fossils from one place, one known age, to approximate the age of a new sedimentary bed with those same fossils elsewhere. So this is what we call using index fossils. Index fossils. Here we have an example of how we can use index fossils to estimate the age of a sedimentary bed. So that if site A over here has these sedimentary layers with these particular fossils illustrated here, and we know the age of these over on this side, because of different igneous layers or volcanic rock or whatever has been used to estimate the age on this side. Over to the other side here, we don't have any of that evidence from igneous intrusions or lava flows or volcanic ash over on this side, but we see some similar fossils. So we assign the age of this bed according to what we know elsewhere on the Earth where those same fossils occur. and the same for the next bed and the next bed, and so on, through our series of layers, sedimentary layers, in this illustration. So that's how we use index fossils to estimate the age of a sedimentary bed. Okay, we've been talking about the fossil record. We had accumulated some information about how we find out how old the different sedimentary beds are that fossils form in. So that's the most important thing, is figuring out how the age of a fossil is estimated to help us understand some of the history of our fossils. So we knew that older fossils are going to be found in the deeper sedimentary beds, and more recent fossils would be found above that. Then we've discovered how we can figure out the age using the isotope methodology to approximate the age of igneous rocks, and how the relative position of the sedimentary beds to the igneous beds help us to estimate the age of the layers. And then we talked about how we can use index fossils to estimate the age of those fossil structures. This information is a little bit different. We're going to talk about missing links in the fossil record. I made earlier reference to living forms that seem to be intermediates between one group and another, that kind of give some support to there being some ancestral form that was a common ancestral form between two dissimilar groups. Here we're going to look at two specific examples that are in the fossil record that are similar to that. The first one, a well-known example, Archaeopteryx. It's sometimes considered the first bird or an early bird form. It had many skeletal features that are similar to reptiles, a more reptilian kind of skeleton, but it had feathers. It was considered a bird that could fly, so it's usually considered the ancient bird, the ancient winged organism, Archaeopteryx. So anyway, it had a tail with extended long vertebrae, a series of vertebrae like you'd find in a lizard's tail, not like modern birds where the vertebrae just have just a few short little vertebrae and comes to a short end, and then the tail feathers, of course, stick out from that. But anyway, modern birds don't have an extended long tail vertebra series like we have in Archaeopteryx. The brain case was quite different, so that it had a smaller cerebellum than the modern birds. Modern birds have a larger coordinating center in their brain for the process of flight. Many other skeletal features, the structure of the digits in the limb of the Archaeopteryx. They had little claws on the end and so forth. That made them more similar to reptiles and the hip and pelvic support structure was not like modern birds, where you see a lot of fusion of bones in modern birds. It's not there in the Archaeopteryx. So anyway, Archaeopteryx, the most well-known example of that kind of intermediate between birds and reptiles there. Another one I like to talk about, Ichthyostega. Ichthyostega is one of now many different fossils that we have become aware of that show a connection between fish and tetrapods. It's the fish-tetrapod linkage that we're talking about there. So we see the beginning of legs that would hold up an organism that walks on land. The first tetrapod kind of evidence there. This was one of the early forms of fish tetrapod intermediates. We now have many other examples of fossil forms that were intermediates between the fish type and the tetrapod type skeleton. There's a very close linkage in many skeletal elements between Ichthyostega and a form of fish known as Eusthenopteron that we'll look at later. So anyway, there's a very close structural similarity there, and there's a lot of similarities between Ichthyostega's initial limb development and other forms of tetrapod limb development we see in the early fossil record out there. So Ichthyostega, the link between fish and early tetrapods, early amphibian types. Archaeopteryx, the link between birds and reptiles.